Hello everyone. In today's lecture, we will start our fourth module, that is boundary layer theory. In this, I will cover the concept of boundary layer, the boundary layer over the flat plate, the minor and turbulent boundary layer, then the concept of the displacement thickness, momentum thickness, we will see, then the boundary layer separation, what is boundary layer separation, and methods to control this boundary layer separation. So we will see first the introduction. This concept of boundary layer was first introduced by the Prandtl in 1904, and since then it has been applied to several fluid flow problems. Okay, so in this, no slip conditions were occurs when fluid flow passed over the solid body or wall. In this boundary layer theory, it was assumed that the flow is flowing through a solid body or a wall, that is real fluid. Okay, in the immediate vicinity of the boundary surface, when this the water was flowing over the solid boundary, the velocity of the fluid increases gradually from zero at its boundary and to the velocity of the mainstream. So that region was called as boundary layer. Now we will see it in a descriptive manner. What is boundary layer? Now in this image you can see there is a solid body. This is a solid body. This body is at rest, and a real fluid flow is flowing with a velocity u over this. Okay, now at the boundaries, as we have assumed that the solid boundary is at rest, so at the boundaries these fluid particles will stick to these boundaries, so no slip condition will occur at the boundaries of the solid body. What does this mean? This means that the velocity of the fluid at the boundary here will be equal to the velocity of the boundary. So here the velocity of boundary is 0 because velocity is at rest. So the velocity of the fluid will be 0. So you can see here, this is the velocity, this pattern here the velocity is 0. But as this fluid particles moves away from the boundary, this velocity will increase and it will result in the variation of velocity with velocity gradient. So as the velocity will be vary at point to point, there will be velocity gradient, that is du by dy. Okay, now we know that the velocity of fluid is increasing from 0 on the stationary boundary to the free stream boundary. Now this velocity is equal to this free stream velocity. Okay, so this variation of the velocity in the direction to the boundary takes place in a narrow region. See, this is the narrow vicinity. This narrow region is called as the boundary layer, and the theory which is dealing with this is called as boundary layer theory. Okay, clear? This is the solid body which is at rest. This is the real fluid, that is free stream velocity, free stream with the velocity u. Now at the boundaries, the fluid particles will have the velocity same as that of the boundary, that is 0, and it will go on increasing away from this boundary. Now this region is known as boundary layer. Now the very thin layer of fluid, this is the very thin layer of fluid, is called as the boundary layer, which is immediately in the neighborhood of this solid boundary, where the variation of velocity is from 0 to free stream velocity, and it is in the normal direction to this boundary. Now in this region, as there is a velocity variation, velocity gradient exists du by dy, and due to this fluid exerts a shear stress on the walls also, which is in the direction of motion. This value of shear stress can be written as tau is equal to mu du by dy. Okay. Now the remaining fluid which is outside the boundary. Now this condition is for the inside the boundary. Now the fluid which is outside this boundary, the velocity outside this boundary layer is constant. See, you can see here the velocity is increasing. This is a parabola, and here it is a vertical line. So here velocity is constant and is equal to u, that is free stream velocity. As there is no variation in this velocity, no velocity gradient will be there, and hence no shear stress will be there. So here in this region above this boundary layer, the velocity gradient is 0 and also the shear stress is 0. Clear about the boundary layer formation when the solid body is kept in rest and a fluid is allowed with a free stream velocity u to pass through it. We will see the various definitions, that is laminar boundary layer, the turbulent boundary layer, what is laminar sublayer. For that we will consider a flat plate. Okay. Now we will consider a flow of fluid having a free stream velocity v. Here the free stream velocity is v. Okay, and a flat plate is used. Assume that this line represents a flat plate, like you can see here. This is a flat plate. Okay, so the flow of fluid with a velocity v is flowing over this smooth thin plate which is flat and which is placed parallel to the direction of this free stream of the fluid. You can see in this figure. So now let us consider the flow with zero pressure gradient on one side of the plate, which is stationary. Now we have seen that how the boundary layer is developed over the solid body. Here the solid body is replaced with a flat thin plate, smooth flat thin plate. So the velocity of fluid particles on the surface of the plate will be equal to the velocity of the plate. Now we have assumed that the velocity of this plate is stationary. Hence, at the surface of the plate, the velocity of fluid will be 0. But as the fluid will move away from the surface of the plate, the fluid is having certain velocity. Okay, as the fluid will move away from this stationary plate, it will have certain velocity. So due to which, and it will have a variation in the velocity, and due to which a velocity gradient will be set in the fluid near to this surface of the plate. Now we have seen that when velocity gradient is developed, shear resistance is also developed, and this shear resistance retards the fluid, slows down the fluid. Thus the fluid with a uniform velocity, that is v, is retarded in the vicinity of this solid surface of the plate. Now this is the leading edge of the plate, so it is retarded in the vicinity of the solid surface of the plate, and the boundary layer region begins at this sharp edge. See, this is the boundary layer. Now at subsequent points, this downstream the leading edge, the boundary layer region will increase. As we will move away from this leading edge, this boundary layer thickness will increase. This is also referred as the growth of the boundary layer. We can see here the boundary layer is forming. Near the leading edge of this plate, where the thickness is very small, the flow in the boundary layer is called as laminar boundary layer. Okay, near this leading edge, you can see from this leading edge up to this layer is called as boundary layer, laminar boundary layer. And this length of the laminar boundary layer is called as the laminar zone. Okay, this is the laminar zone. Now, this distance from the leading edge can be obtained from the Reynolds number, because this is a laminar boundary layer, and for laminar you can use Reynolds number as 5 into 10 raised to 5 for a plate, because up to this Reynolds number the boundary layer is laminar. Now, if you have the values of the velocity v and the viscosity, this distance, that is laminar zone distance, can be determined. So this is about the laminar boundary layer. Now if a plate of a longer length is used, the thickness of the boundary layer will go on increasing in the downstream direction. See, here the thickness of the boundary layer is less, here the thickness of the boundary layer is increasing downstream. Then the laminar boundary layer becomes unstable. Due to this, the laminar boundary layer will become unstable, and the motion of fluid within this boundary layer will also become unstable. It will get disturbed, it will get irregular in pattern, and this will lead to the transition from the laminar boundary layer to the transition boundary layer. This short length over which the boundary layer flow changes from the laminar boundary layer to the transition boundary layer is called as transition zone. This length is called as transition zone, and this distance can also be calculated by using the formula, Reynolds number formula. Further downstream the transition zone, the boundary layer is turbulent and is continue to grow in thickness. So here further it will go in increasing. Here it is a transition region, but the thickness goes on increasing. So here the turbulent region, the thickness will go in increasing. This layer is called as turbulent boundary layer. Now in this turbulent boundary layer, we can see the formation of the viscous sublayer, that is laminar sublayer. Now we will see this. What is laminar sublayer? This is the region which is in this turbulent boundary layer, which is adjacent to this solid plate. In this zone, the velocity variation is influenced only by the viscous effect. Okay, though the velocity distribution will be parabolic in this region, but in view of the very small thickness, we can reasonably assume that the velocity variation is linear. Though we are seeing here the velocity is parabolic in nature, the velocity distribution, but in the laminar sublayer it is assumed to be linear in variation, and so the velocity gradient can be considered here as constant. Therefore the shear stress in the laminar sublayer will be constant and will be equal to the boundary shear stress, that is tau. Thus the shear stress in the boundary layer will be similar to that as shear stress to the laminar sublayer. Now we will see the definition of this boundary layer thickness. The boundary layer thickness is defined as the vertical distance from the plate to a point where the flow velocity reaches 99% of this free stream velocity, that is u0. So it is the vertical distance from a plate to a point on the boundary layer where the velocity reaches the 99% of the velocity of free stream.